Great. So then let me briefly introduce Hasan first. So Hasan Maruf is a PhD candidate in computer science and engineering at the University of Michigan Ann Arbor. His research goal is to address the practical challenges of memory disaggregation to improve application performance and data center resource utilization. During his PhD, he is leading a comprehensive solution to address the host level, network level, and end-to-end aspects of practical memory disaggregation. Let's get started.
So hello everyone, I'm Hasan. I am a final year PhD student from the University of Michigan. Today I'm going to present my work on transparent memory management for CXL and both systems. So this work is done in collaboration with Meta and currently being used in their production servers. So before I start, let's first talk about why CXL memory matters. Why CXL memory matters? What are the properties and how Linux default page placement mechanism work for CXL memory. So memory intensive applications are widely being used in many cases, like in low latency services and data intensive analytics. These applications have very good performance when their whole working set fully fits into the host machine's physical memory. However, if the host machine does not have enough memory, then these applications need to go through expensive disk operations. As a result, they face severe performance loss. To illustrate this, we run TPCC workload on an in-memory database system, VolDB, and measure its performance in terms of throughput per second. Here, the higher throughput means better performance. As you can see, if we take away 25% memory from the host machine, VolDB loses almost 80% of its performance. If the host machine can support only 50% of its performance, 50% of its memory demand, then VolDB hardly performs. In this case, VolDB loses almost 95% of its performance. Same thing happens for latency sensitive applications like PowerGraph. We run PageRank algorithm over Twitter dataset on PowerGraph and measure the end-to-end completion time. Here, lower completion times means better performance. Similar to VolDB, PowerGraph loses almost 75% of its performance at half of its peak memory demand. So this is obvious. You lose your memory and this will cause you performance drop. But this performance loss is highly disproportional to the memory loss. As you can see, half of the memory loss causes almost 38 times performance loss for VolDB and 4 times performance loss for PowerGraph. And to resolve this, in cloud, when people run memory intensive applications, users usually allocate more memory than necessary. This puts us in a situation between a rock and a hard place. On one hand, if we allocate less memory, you will face severe performance drop. And on the other hand, over allocation causes underutilizations of the memory in the cluster. For example, in most of the big clouds like Google, Alibaba, or Meta, on average, 30 to 40% of memory always remains underutilized. More importantly, this underutilization is not uniform throughout the whole cluster. Some machine can be under severe memory pressure, while the others may have significant amount of free memory. Flexibility in memory subsystem design and fine-grained control over the memory bandwidth and capacity can solve this problem to a great extent. However, we cannot design a flexible memory subsystem with today's server because CPU and memory are tightly coupled. They are usually connected through a specific DDR channel. To increase the memory capacity, we need to increase the total number of memory channels and populate DDR DIMMs at power of 2 granularity. Besides, all the memory nodes to the CPU are of homogeneous properties. We cannot mix and match different memory technologies with different cost per gigabyte and bandwidth versus latency profiles. So when a new generation of CPU is available, we need to upgrade the DRAM accordingly. And for that, the previously owned DRAM then becomes obsolete and it increases the total cost of ownership of the data center. And it also increases the power consumptions of the data center because newer generations of hardware may sometimes have higher power demand. So CXL enables fine-grained server design by providing a flexible interconnect between CPU and memory. Through CXL interconnects, memories of different DDR generations can coexist together and enable different capacity to bandwidth ratio. You can run DDR5 on the newer CPUs, while your earlier generations of DDR2 or DDR3 can also be connected to the CXL interconnects, and it can reduce the TCO of the data center and also may reduce the power consumptions. And we can also add cheaper and low power memory technologies in parallel to the DDR ones. CXL also provides the opportunity of near memory computations through attaching multiple accelerators. The prime benefit of CXL memory is it offers a byte addressable memory in the same physical address space. Applications can transparently allocate memory using standard memory allocation APIs. CXL memory access is in cache-line granularity, and the underlying hardware maintains the coherency and consistency. Besides, memory access bandwidth is almost similar to the DDR channels. In some cases, the NUMA bandwidth can be even better than the dual socket system. The memory access latency is also similar to NUMA access latency of today's dual socket systems or multi-socket systems. So it is expected that CXL will add extra 70 to 80 nanoseconds over the NUMA access latency in a dual socket system. However, these extra hundreds of nanoseconds of latency can often be an issue for the production applications if memory is managed inefficiently. To illustrate this, we run 3 production applications in Meta's server fleet with large CXL memory capacity. Here, 80% of the total memory capacity of the server comes from the CXL memory. So default Linux cannot automatically move pages between different NUMA nodes, and that's why when the CPU address memory gets filled, new pages get allocated to the CXL memory and gets trapped there forever. And this causes 14% of performance drop for cache application. Autonoma is another Linux approach to manage the tiered memory, to manage the hot memory between multiple NUMA systems. So it can promote hot pages back to the memory node attached to a CPU where the process is running. However, when the CPU address faster memory is smaller in size and always remains overloaded with new page allocation request, hot page promotion from CXL memory gets postponed, and at that point, NUMA's benefit disappears. That's why even with Autonoma, the performance loss of the cache applications is 10% of its 10% less of its actual behavior. This observation holds for other applications like web applications or data applications, data analytics applications running in Meta's today's production servers. So efficient management of CXL-enabled heterogeneous memory subsystem is a must to maintain the performance. However, doing so in a transparent manner is challenging for some reasons. The most important challenge is how we are going to manage the hot fraction of an application's working set. More hot pages served from a faster memory node means better performance. And to do so, we need to put new memory allocations to a CPU address faster memory node. But this may not always be possible because of the capacity constraint on CPU address node. For this reason, we need to move warm and cold memory efficiently to a slower memory tier. And at some point, if the pages moves through the slower memory tiers become hot, we need to promote them back to the faster memory tier for better performance. All these hot, warm, cold page temperature detections and page movement needs to be lightweight and of minimal overhead. Apart from that, applications may have sensitivity towards different page types. Like some applications can be more sensitive towards anode pages, while others can be more sensitive towards the cache one. So applications, our page allocation policy can significantly help in many cases. The next challenge is how we are going to decide applications for CXL systems. Not every kinds of applications can be benefited from such heterogeneous systems. And to find the appropriate applications, we need to characterize their working set. What fractions of their memory remains hot, warm, or cold, how long a page survives, and how frequently they get accessed, and so on. And in this regard, we need a specialization tool to figure out what fractions of a memories, what of an application's memory remains like hot or cold. And in this regard, in this talk, for brevity, I will mostly focus on the first challenge, that is how to efficiently manage the hot pages transparently. And to do so, we designed TPP, an in-kernel transparent page placement mechanism for heterogeneous tiered memory systems. It employs a lightweight demotion mechanism for warm and cold pages, which is complemented by an efficient hot page detection and promotion mechanism. TPP decouples existing Linux page allocations and reclamations logic to reduce the latency overhead. And besides, it introduced new page allocation policy that can be useful for certain types of workloads. TPP is transparent to application. Although it is mostly designed considering CXL-enabled system, TPP can be used even on traditional NUMA systems or any tiered memory subsystem. And this work is currently being used in Meta's production environment for about a year. it also been accepted in HCM'23. So the patches for TPP has been published for Linux community, and they have been already incorporated in Linux since Linux 5.18. So before I discuss TPP's component, let's first see how page placement happens in today's Linux. In Linux, every memory node maintains 3 watermarks like mean, low, and high. And this is to determine the loads on those NUMA nodes. These watermarks indicates the threshold for total number of free pages within a node. So the default allocation policy is allocate page on the memory node attached to the CPU where the process is running. If the available free page of that node goes below the high watermark, Linux kernel marks the node as full and stops allocating new pages to that node. It starts reclaiming cold pages to get some free memory pages, and swapping to disk is the default reclamation mechanisms in today's Linux. And this is a terribly slow process. So while reclamation is happening, new allocation goes to the next available node, and later access to those pages have higher latency overhead. However, when the reclaimer finds enough free pages to support the high watermark, new allocations can happen again on that local node. It appears both allocations stop and reclamation start is depending somewhat on the same watermark. And as reclamation is a slower mechanism, if an application has extremely high allocation request, allocations on the local node will halt every now and then. And in that case, more help pages will end up in the remote node, and it will cause more high access latency because they are being served from the remote node. So to address this, TPP initiates a faster demotion path. So instead of paging, TPP allows migrations to remote node during reclamations, and this is orders of magnitude faster than paging. So to do so, TPP introduces a demotion list which tracks the inactive and warmer pages of a node. And we utilize the existing active inactive LRUs of Linux kernel for a page age management. So during a reclamation process, TPP initially scans the inactive file and anon LRUs to find the necessary numbers of pages to be freed. If that's not enough, then it moves to the active file list first and then active anon list. After finding the candidates, TPP initially tries to migrate them to the slower memory tier. And if the migration fails for any reasons, like there is no memory on that node or the node is unavailable, TPP falls back to the traditional swapping mechanism. And this helps to maintain the backward compatibility to the generic swapping systems of Linux. So TPP also allows faster memory allocations through an optimized data path. It decouples the allocations and reclamations logic mentioned earlier. We introduce 2 separate watermarks specifically responsible for allocations and reclamations. So now in Linux, you will find 4 watermarks. And these reclamation watermarks can be configured to trigger early, much earlier. In TPP, when a node's free memory goes below its capacity by X%, we trigger the demotion process to move cold pages to the CXL node. And one can configure it from the user space to define based on the application's need or the system's requirement. And when this reclamations happens, allocations to the local node can happen simultaneously as long as the free memory does not cross the allocations watermark. This allocations watermark is kept lower than the reclamations one, so that allocations can happen even if a smaller amount of free memory is available. This extra headroom allows reclamations to catch up any burst in allocation request, which eventually helps more pages ended up in the faster local node. So the high level idea is when allocations is happening, we'll first try to make most of the allocation place into the faster memory tier, and then maybe whatever goes into the slower tier, we'll try to promote back to the faster tier later. So now we talk about the promotion mechanism. So I told earlier, Autonoma is a Linux feature which helps to identify the trapped hot pages of a remote CPU node and brings it back to the local node to avoid the Luma latency. And to do so, it periodically samples a subset of a process memory address spaces and poison those page flexes. So whenever a local or remote CPU tries to access the sample pages, it causes minor page fault. And we call this NUMA hint fault, as it gives information on which CPU is trying to access the page. So if a remote CPU tries to access the page, Autonoma tries to migrate the page to the CPU's local node. And the helpful assumption is the CPU will access the page later. And for those accesses, it can avoid the NUMA latency. However, if the target node does not have enough memory, it means it is if its number of free memory goes below the high watermark, this migration attempts will be failed, and the page will be trapped to the remote CPU node, and subsequent access will have the high access latency. And at that point, autonomous benefit disappears. Rather, it causes extra overhead due to scanning and hinting faults. So in TPP, we utilize the concept of autonoma, but make it much optimized to hide the overhead and pitfalls. We don't need to promote pages that are already in the faster tier memory node. So we just don't sample the faster memory tiers. So if we can serve almost all hot traffic from the faster tier node, the overhead of autonomous scanning and page fault reduces significantly by the simple tweaking. So a NUMA hint fault may come from an infrequently accessed pages too. For example, one pages can be moved to the slower memory tier and can be accessed once in every hour. In such cases, moving the page back to the faster memory tier can be a waste because it will eventually be demoted back. And to reduce this wastage, we consider a page's activeness before promotions. If a page is in its active LRU during a NUMA hint, that means it has a higher chance of being active later on. And then we actually move the page to like the faster memory tier. But if the page is not in the active LRU, then after a NUMA hint fault, we will just move it to the active LRU. And then during the subsequent accesses, if we find the page still in the active LRU, we will migrate the page to the faster memory tier. So this simple tweaking reduces almost 10 times extra traffic over the NUMA nodes because of this promotion, ping pong promotion things. And as NUMA kernel separately maintain the anon and file LRU, inclusions of LRU mechanism during promotion by default gives different priority towards different page types. Like if anon page types are high, if file pages are being accessed randomly, the chance of finding a page on the active file LRU during a second hint gets somewhat lower. On the other hand, if a small amount of anon pages get frequently being accessed, then we will have a higher chance of finding the page in the active anon list. So there's some workload error allocation policy on TPP. For time constraint, I am like skipping those things. And TPP appears in today's Linux as a new autonoma mode. One can use NUMA balancing normal modes to enjoy today's vanilla autonoma mechanisms, which is like the backward support. And for tiered memory systems, you can have this NUMA balancing memory tiering mode to enjoy the TPP's behavior. And in terms of evaluations, we evaluate TPP on Meta's production environment with live traffic for different types of applications. And we use two prominent caching applications, one social media applications and one data warehousing and analytics applications. We find that in our evaluation, TPP optimized allocation and data movement policy can handle burst even more effectively. Because of its watermark decoupling, TPP allocates 1.6 times more pages to the faster memory tiers. And always having a free headroom in the fast memory tier can allow TPP more promotions of trapped hot pages. Promotion in TPP is 30 times faster than its counterparts. And in terms of overall application performance, TPP improves the performance of all the applications of a default Linux and Autonoma and some other state-of-the-art of tiered memory management systems. Based on an application access pattern, TPP can improve the throughput by up to 17%, which is a huge gain for any hyperscaler data center. And in summary, TPP is a transparent page placement mechanism for tiered memory system that is orders of magnitude faster during demotions and 30 times faster and 1.5 times better hot page promotions is involved with TPP's because of TPP's features. With its 1.6 times better page allocations and workload page allocation policy, TPP helps applications maintain a better performance even with a smaller CPU attached memory. And that's all from me. If you have any questions, I will feel free to take them. And yeah.
For this talk, if you have any question, you just go there and then directly ask.
Sorry?
No worry, we are talking to the audience.
Any questions?
I have a question.
Yeah, sure.
You should directly.
Yeah, my question is, in your case, you know, when we business working with a huge page, maybe the allocation policy is going to be different. You know, how can you handle this huge page cases? Yeah, thank you.
Yeah, so huge page allocation is a there can be a different like we try to make TPP generic for the any page type, but this is mostly designed for 4 kilobit pages. Huge page has different types of necessity, like when you promote or demote a huge page 2 megabytes of pages, you need to be more careful. So TPP needs more optimizations for handling the for 2 megabytes of pages. I can say it can work on 2 megabyte pages, but it will not give you the optimized or best performance for huge pages. For huge pages like 2 megabytes or 1 gig, you need some special considerations. And in Metas productions, we basically consider 4 kilobit pages because huge pages are handled in a different manner there. So it is assumed that huge pages will be always remain in the faster memory tier. So that's why one reason is making TPP more 4 kilobit granular is because of generic purpose, and also this is not the main concerns of this particular Metas environment. But yeah, for 2 megabytes or even larger pages, you need some special considerations for making TPP more optimized.